Good morning guys, welcome to today's worked exam answer video, where today I'm having a look at an AQA Arrhenius equation question, the content of which would also be applicable to those of you studying the AQA A specification. And in this particular Arrhenius question, we're doing a rearrangement, but there's a little bit more to do in this question because unlike questions that came before this one, they haven't given us the Arrhenius equation in the format that we need it to be able to calculate what they're asking us to calculate. And prior to this, they would always give you, or they always did give you, the variation of the Arrhenius equation that you needed. And this was the first time they didn't do that. So we either need to be able to go from this version that they have given us to the alternative version, which we can then rearrange in order to calculate temperature, or we just need to learn both of them, and it depends on how comfortable you are with the maths. I'm not going to say that one way of doing it is better than the other. If you do feel comfortable going from this to the other, makes sense, but I'm going to show you how to do that now. Now, in terms of how I know that this version of the Arrhenius equation isn't going to be the right one for us to use, the question's asking us to calculate temperature, and currently temperature is on the bottom of a fraction where the whole fraction is up as a power of the mathematical constant E. And there's no way we're going to be able to rearrange that to get T equals unless we get rid of this mathematical function E, which is where mathematicians will perhaps feel a bit more confident with this. However, the alternative version of the Arrhenius equation gets rid of the E, and it therefore brings all of that fraction out of the power into the main body of our equation, and then we can rearrange it from there. And it's still not a very nice rearrangement, but it is at least doable. So in this particular question, we have been given a version of the Arrhenius equation. We have also been given the activation energy, annoyingly in kilojoules per mole. We have to remember that the standard units for activation energy is in joules per mole. So as you will have seen me do before, I tend to do all of my conversions straight away, and I should probably be able to do that in my head, but I don't want to get it wrong. So 34,500 joules per mole. And it's really interesting because if they ask you to work out activation energy, they'll ask you to convert your answer into kilojoules per mole. Obviously, if we need to use the activation energy, they're going to give you it in kilojoules per mole. So it's usual that we have to convert activation energy in some form. We've also been given the Arrhenius constant A, which we'll never need to convert. It's always going to be in the same units as the rate constant K. So we just need to be able to sub that in. And then we're told at temperature T1, the rate constant is 2.48 times 10 to the 8 seconds to the minus 1. Again, we know the rate constant has different units depending on the overall order of our reaction, so we're not going to need to convert that. It might be that you have to work that out in a previous part of the question. Obviously we didn't here. And then our job is to calculate T1. And then for AQA students, you'll always be given the gas constant in questions when you need to use it. For OCRA students, it'll be in your data booklet, so you'll need to, I guess, twig that you need to look that up. So we've only needed to do one conversion. If you were given a temperature, again, it's likely they'd give you it in degrees Celsius and you would have to convert it into Kelvin, but we're trying to work out temperature here, so we're going to give our answer in Kelvin. Again, it might be that if you are working out a temperature, they then get you to convert it into degrees Celsius, just to be irritating. So in terms of how we're going to convert our Arrhenius equation, so lowercase k for the rate constant is equal to the Arrhenius constant A, and then E is our mathematical function, and then that is all the minus EA over RT, a power. So it's quite tricky to show that clearly. It's ended up quite small in the exam question, but all of that is up to the power. Now, on most calculators, although I did learn the other day that not every single calculator that a student might use, this is true for. But when I find my natural log, the ln button, to the, like if I then press shift, there's the E function. Now that is helpful because that kind of hints at the fact that the natural log and E are the mathematical opposites of each other. Just like for those of you who've done your pH calculations, doing like minus log of the H plus concentration gives you pH. If you have pH, we do 10 to the power of minus pH, and they are also on the same button. It might be that your calculator, they're not on the same button, but ln, the natural log, and E, they are mathematical opposites. And that's important because if I want to therefore get rid of the E to bring all of this out of the power, I'm going to have to take the ln of everything. So if I do that, I end up with the ln of K, the rate constant, being equal to the ln of the Arrhenius constant A, and then A in this equation is multiplied by E. And again, mathematicians will know that when we take logs of things, if you've got two things multiplied together, the product rule tells us that we would then have ln A add the ln of E to the power of minus EA over RT. And this is where obviously if you're not comfortable with the maths, you might just be happier learning both versions of the equation. Now, the whole point of me doing this is that then the ln and the E will cancel each other out. So it's like doing times 5 and divide 5. There's no point. You're just going to get back to where you started. So we can therefore cancel those out. This then can't stay as a power because it's to the power of what? So that then means we can bring that out of the power into the main body of our equation, and then we will have the ln of the rate constant K is equal to the ln of the Arrhenius constant A, and then we're going to be adding minus EA over RT, and if we're adding a negative, we're just going to be subtracting, so that then becomes minus EA over RT. So that is the alternative version of the Arrhenius equation that you may just want to learn if you're not comfortable with the maths. Now from here, we can rearrange this to be able to calculate temperature. Like I said, it's not the easiest rearrangement, but it is doable. Now personally, I would be taking the minus EA over RT across to the left-hand side so that it becomes positive, and then taking the ln K to the right-hand side. Yes, that will then become ln A minus ln K, but I'd rather have this as a positive. So essentially I'll swap them over for my first step. So that would then give me EA over RT is equal to the ln of A minus the ln of the rate constant K. And then temperature's on the bottom, so I'm going to have to take both R and T over to this side and multiply the ln A minus ln K by R and T. So I'll do that next. And in some questions you will need to do this and rearrange this version of the Arrhenius equation to figure out activation energy. And at this point you would obviously be done and you could then start subbing in your numbers. However, because we want temperature, we're then going to have to take all of the other stuff in front of the temperature and put it underneath the activation energy on the other side. So it's going to be the activation energy divided by the ln of A minus the ln of K times by R is equal to temperature. So like I said, not the nicest one you'll ever rearrange, but it is doable now. And at this point, we're then just subbing in our numbers. So that is by far and away the hardest part of this question. Obviously, if we don't know to convert our activation energy, we're going to get a slightly dodgy answer. But that is, yeah, the fundamentals. So in terms of then subbing in, we have got activation energy 34,500, and then we're going to be dividing that by the ln of A, which is 1 times 10 to the 12 minus ln of the rate constant, 2.48 times 10 to the 8. And annoyingly, I've not left myself enough room to do this, so we'll put all of this in square brackets, because that then needs to be times by the gas constant, 8.31. So all of that is on the bottom of my fraction. I'm very sorry that I've not presented that in a better way. But from there, it's up to you whether you want to put all of that into your calculator in one step. I probably wouldn't do that. I would probably figure out what the denominator is first by doing the ln of 1 times 10 to the 12, take away the ln of 2.48 times 10 to the 8, times 8.31, and then I would do 34,500 divided by my answer to get me a temperature of 500. I could do it as 500.1, but if I have a look at all the significant figures in the question, 3, so 500 Kelvin. Answer. Just to show you that it does work out, obviously if you put it in your calculator all in one step, I think the biggest concern I would have about that is making sure we've got the right number of brackets in. I don't want to say that the calculator might mess it up, because obviously it'd be me messing it up, but there's just a lot to kind of then do all in one go. So ln of 1 times 10 to the 12, take away the ln of 2.48 times 10 to the 8 times 8.31, and I definitely don't have quite enough brackets in there. Same answer. But yeah, that would be how we would go about doing that question. So as I said, it's either a case of knowing both of these, or being able to go from this version to this version and knowing how to do that, being comfortable then rearranging this version to get either activation energy, because that would be needed in certain questions, or temperature as we needed here, and then remembering activation energy standard units is in joules per mole, subbing your numbers in to get your answer. And as with any calculation, always look at the number of significant figures for all of the values in the question and follow suit. Hopefully that's all made sense. Any questions, please let me know. And yeah, hope you're all well and revision's going well. And if there are any requests, also please just let me know. Have a really good day, guys.